Welcome to lecture 3 in week 6 of machine learning foundations. This is the last leg of linear algebra, where we'll look at a very important topic, principal component analysis, which is a dimensionality reduction method. Now we'll start in this. PCA has two viewpoints. You could view it as either minimizing the so-called reconstruction error, which we'll define concretely, or you could also see it as maximizing variance of the data. And we'll start with the first viewpoint. In this lecture, we'll define what the reconstruction error is for a given set of data points, and then try to understand what PCA does. And we'll look at an example subsequently. And this is a two-part lecture simply because PCA discussion will take longer than one video. So we'll continue this discussion in the next lecture also, and then look at an example to see how PCA is minimizing the reconstruction error. Subsequently, we'll look at the second viewpoint, that is of PCA as maximizing variance, and show that how these two viewpoints are equivalent. You could view PCA as either minimizing the reconstruction error or maximizing variance. So we'll discuss that in the subsequent lectures. Principal component analysis is a method that is used for feature selection in the context of a machine learning problem. And the idea of feature selection, to put it in very simple words, is you start with as many features as you can collect. Now this just means that you're going to have high dimensional features, and then what you do is you use some methods for dimensionality reduction. PCA is a very popular alternative. So what you do is then find a good subset of features. Now this is the broad problem of feature selection. And what does PCA main idea? The main idea behind PCA is project given data onto a lower dimensional subspace such that PCA has two interpretations, and both are valid in the sense one is a project onto low dimensional space such that reconstruction error, we'll make all of this precise, reconstruction error is minimized, or alternatively variance of the projected data is maximized. So what PCA does is you can derive the PCA algorithm by looking at variance of projected data. Projected data is maximized. So both are valid. So we'll first look at PCA, the main idea, by understanding how it minimizes the reconstruction error. For this, here is a problem formulation. Suppose you are given a data set which is x1 until xn, where each xi belongs to the three-dimensional Euclidean space. Now this is given. This is given. So what's the goal? Project let me call this data D. Project D onto a m-dimensional subspace. Now, important, m is an input parameter. You fix this parameter beforehand. Imagine you fix a lower dimension, you fix the dimension of the space, subspace that you want to project onto. And now given this parameter, you want to find the best m-dimensional subspace to house this data. So let's, so we'll arrive at the PCA algorithm by looking at, in a constructive manner. I won't specify the algorithm and try to deconstruct. Let's start with the problem itself. So given this goal, so let's me say arriving at the PCA algorithm or the build up to the PCA algorithm. So let B equals U1 be a orthonormal basis for a m-dimensional subspace. Let's understand this. So the way to understand this is fix a subspace and then find the best projection. Okay, that's what we do. Later we will understand how to choose the subspace optimally. So there are two things to it. For the sake of understanding, imagine you are given m vectors in some arbitrarily chosen m-dimensional subspace, and now given this m vectors, you want to find the best projection of the data. So let's do this. So now what we can do is you can extend B to a basis for the original d-dimensional subspace that houses the data. So this is let this extended basis be, you have u1 until um, and then you add the remaining d minus m vector, so um plus 1 until ut. So this is a basis. It's into an orthonormal basis. Okay. Now given this basis, denote this as B prime. Now this is a full basis for the d-dimensional space. So any vector x belonging to Rd can be written using B prime as follows. Now how do we write this? Alpha 1 u1 plus so on alpha d ud, where how do you figure this coefficients or the scalars, where alpha j equals x transpose uj for j equals 1 to d. This is fairly straightforward. This is linear algebra 101. Given a basis, orthonormal basis, how can I express any vector in a linear form? Now, so expressing each data point xi in the set B that we have, x1 to xn, using B prime, we have xi equals summation j equals 1 to d xi transpose uj times uj. Now this is the original xi. This is the original data point. Now how do we project this onto the m-dimensional space? So we want to approximate xi by xi tilde as follows. So how do you do this? What you do is, let's define xi tilde as summation j equals 1 to, we'll split this into some terms up to n and something beyond. Now I'll call this zij. These coefficients are something that I need to figure. This beta j. So j equals m plus 1 to d. Now this is the projected data point, a point that belongs to the m-dimensional subspace, yeah, that is belonging to the m-dimensional subspace. Now we need to figure the coefficients. Now next step, find optimal zij's and beta j's for all ij. Yeah, I'll just leave it. Yeah. So how do you find this? For this we mean to minimize a certain square error. So let me define this. So the error that you want to minimize is j equals 1 by n summation I equals 1 to n this is what you want to minimize. Yeah, so want to minimize j over this coefficient zij's, beta j's. This is what you want to do. Now before we go on to minimizing this, I'll just rewrite this objective by expanding the square. So this is nothing but 1 by n summation I equals 1 to n, the norm of what is xi. Xi is summation j equals 1 to m xi transpose. So just look at xi and xi tilde. So we just have to take the difference of xi and xi tilde, and so this is xi transpose uj minus zij into uj. So this is the first term, plus j equals m plus 1 to d, again xi transpose uj, but this time we have a beta j into uj. Now this is what you have in the norm, but what is important is this simplifies if you expand the norm. So what happens is this is like if you expand this, so recall the L2 norm. I hope you know what the L2 norm is. So I'll just write out the main conclusion, then try to argue this is really the case. Plus summation j equals n plus 1 to d xi transpose j minus j square. So the question is why is this true? Why? Okay, why? Simple case. Imagine you have norm of a, say, c1 u1 plus c2 u2 square, right? Now this is going to be c1 square norm u1 square plus c2 square norm u2 square plus 2 c1 c2 u1 transpose u2. Now if u1 comma u2 is orthonormal, then norm ui equals 1, I equals 1 comma 2, and u1 transpose u2 equals 0. Now this just means that this is equal to c1 square plus c2 square. And the same thing is happening here. Now if you look at this, let me call this term 1 and call this term 2. Then what you have in star is norm of, some c1 u1 until, you can extend this logic. Is let's say c m u plus something else, which is c m plus 1 u m plus 1 until some constant. It does not matter what it is, ut. Now this square, now this is going to be equal to just the individual square, simply because when I take, I can extend this logic here, I can extend this logic all the way here. So this I would get c1 square plus cm square plus cm plus 1 square plus cd square, which is let me call this double star, and this is the form of double star. Simply because you have an orthonormal basis, the cross terms vanish, and for each of the individual terms, since ui's are all unit norm, you get the individual squares. So we have, so let's get back to PCA. So what we have is j equals 1 by n summation I equals 1 to n summation j equals 1 to m xi transpose uj minus z ij square plus summation j equals m plus 1 to d xi transpose uj minus beta j square. Now to minimize j over z, so we still need to figure what are the best coefficients, zij's and beta j's. We find the partial derivatives and equate them to 0. So what are the partial derivatives? Let's do dou j by dou zij. If you see zij appears only in one term in this entire j. And now if you take the derivative of that, you just get 2 times xi transpose uj minus zij equals 0, which just implies the most important thing, zij equals xi transpose uj. So we got a first question. Now proceeding similarly, you want to do something to beta, so let's do dou j by dou beta j. Now I have to equate this to 0, so this beta j appears within a summation. It's not just one term, it's a summation. So what I would get is 1 by n summation I equals 1 to n. Okay, let me write it. This implies this. Okay, so I'm going to equate this. Xi transpose uj minus beta j. Okay, this is what will be equal to 0. This just implies, if I rewrite this beta j, one by n summation xi equals 1 to n transpose uj. This is what you would get. Okay. I'll denote this as x bar transpose uj, where x bar is the mean of the data, which is 1 by n summation xi equals 1 to n. So this is the expression. Beta j is this. You take the average point and take the dot product with uj, so the average point is denoted here. Okay, so clubbing this all together, substituting back in xj tilde, so for a given m dimensional subspace spanned by u1 to um, the best projected data is given by xi tilde is equal to summation j equals 1 to m. The first m points coordinate, you need to have zij, so which is xi transpose uj into uj, and for the remaining j equals m plus 1 to t, you take the average point x bar transpose uj into uj. Just a minor note, if the data is already centered, then x bar equals 0 and the second term vanishes. Okay. The data is already centered, which is what usually people do when you do PCA. And you can take x bar out of the equation, and then what you are left with is just the first term here, and it's clear that it's in a n-dimensional space. Now let's proceed and figure which is the best, but which are the best use to pick. But before that, let's understand. So from the foregoing, what you have is xi minus xi tilde equals, if you look at xi and xi tilde, the first m terms coincide. Just go up to xi. It's each is xi transpose uj,
Now up to m, if Zij is the same as Xi transpose Uj up to m, then the first m terms cancel when I take the difference from Xi to Xi tilde, and I'll be left with the d minus m terms. So Xi minus Xi tilde is nothing but summation j equals m plus 1 to d Xi transpose Uj, this is what would be in Xi, minus x bar transpose Uj into Uj. This is Xi minus Xi tilde. Now using the logic that I have said before, again when I take the square, norm square, then what I would get is individual nt squares, which is Xi transpose Uj minus x bar transpose Uj square. This is the same as j equals m plus 1 to d, a minor rewrite, xi minus x bar transpose uj whole square. Now this, for this this equality follows by the logic that I have explained here, the same as this. Yeah, when you take the square, you get the individual coefficient squares, and the individual coefficients are xi transpose uj minus x bar transpose uj. So it will be the sum of squares of these coefficients, simply because again you have an orthonormal set. Um plus 1 until ud is still an orthonormal set. Yeah. So what we have is, with optimal set ij comma j, the square error becomes, what you have is, let me call this j star, the optimal, because it's optimal for a given 1 by n, summation I equals 1 to n, summation j equals m plus 1 to d, and then just xi minus x bar transpose uj square. This is what we have. We are going to further simplify this. Now, if I continue simplifying this, then what I would get is 1 by n. I'm going to interchange the summations. So let j equals m plus 1 to d, summation I equals 1 to n, and then this square can be written as dot product with itself, which is writing xi minus x bar transpose uj, this product with xi minus x bar transpose uj. Now this again I can write this as summation j equals m plus 1 to d, I equals 1 to n. So the reason I'm doing all of this is I want to extract something with just xi and x bar. I want to extract a matrix with just xi and x bar outside and keep the uses in a much simplified form, so that I can figure how to find this u1 to um, and so that a certain the projected error is minimized. So to do that, let's continue this calculation. So what I have is this transpose, the basic rule is uj transpose xi minus x bar into xi minus x bar transpose uj. Okay. Now this I can write as summation j equals m plus 1 to d, and I'm going to bring the uj outside because it's in a summation with variable I here. So the uj can come outside, this can come outside, the other uj also can come outside. I'm just left with the rest. So uj transpose and then I'm going to write this as 1 by n summation I equals 1 to n. This is a very important matrix that will come up now. Xi minus x bar transpose, whole thing into Uj. So I'm going to call this matrix C. Summation j equals m plus 1 to t Uj transpose C Uj, where C is this matrix, which is equal to 1 by n summation equals 1 to n xi minus x bar xi minus x bar transpose. So this is what we have as J star, and now you need to find the best use using this formulation. So we want to focus on this form and try to figure what is the best way. So let's consider a very simple case.
So the summary of today's lecture. In today's lecture, we started the discussion of PCA, and we are going with the PCA as minimizing the reconstruction error viewpoint in this lecture. So we, for a given set of data points in some d-dimensional space and an input parameter which is necessary for PCA, which gives the dimension of the space where you want to project the data onto. Given this parameter say m, we are trying to understand what's the best way to project the data onto this lower dimensional space with this input parameter, so that the reconstruction error is minimized. So we defined what reconstruction error is and started the discussion about how we can go about finding the best lower dimensional space so that the reconstruction error is minimized. This is a two-part lecture. We'll continue this discussion in the next video also, and then we'll be able to arrive at the final PCA algorithm, which gives you the recipe for finding this best m-dimensional subspace onto which you can project the data onto, so that the reconstruction error is minimized. In the next lecture, we'll also, after giving the recipe for PCA, we'll look at a very simple example to illustrate the ideas of the PCA algorithm.